Welcome back. We have learned that a matrix is a transformation of space, and that multiplying matrices composes transformations. The natural next question is simple: can we go backwards? If A scrambles space, is there a transformation that unscrambles it? That transformation is the inverse of A, written A inverse. Apply A, then apply A inverse, and every vector returns exactly to where it began. Algebraically, A inverse is the matrix that multiplies A back down to the identity from either side. Today we do three things. First, the famous 2x2 formula built from a single number called the determinant. Second, the universal algorithm that works for any size. Write the matrix beside the identity and row, reduce until the identity migrates across. Third, the grand result of the whole chapter, the invertible matrix theorem, which reveals that a dozen different conditions are all secretly one condition. Let's begin with what an inverse even is. Let's pin down the definition. A square matrix A is called invertible if there is another matrix, written A inverse, such that A times A inverse equals the identity and A inverse times A also equals the identity. Both orders give the do-nothing matrix. A few facts come immediately. Only square matrices can have inverses. A transformation between spaces of different dimension can't be cleanly undone. When an inverse exists, it is unique. There is exactly one undo matrix, and a square matrix that has no inverse gets a special name. We call it singular. Now the payoff, and it is large. Recall a system of equations is just A times x equals b. If A is invertible, multiply both sides on the left by A inverse. A inverse times A is the identity, which leaves x alone, so x equals A inverse times b. That is a unique solution, and it exists for every possible right-hand side b. Inverting the transformation solves the system in one stroke. The rest of the episode is about when the inverse exists and how to compute it. For 2x2 matrices, there is a formula worth memorizing. Write A with first row A, B, and second row C, D. The key quantity is the determinant of A, defined as a times D minus B times C, the product of the diagonal minus the product of the off-diagonal. If that determinant is not zero, the inverse exists and is given by a tidy recipe. Swap the two diagonal entries A and D, negate the two off-diagonal entries B and C, and then divide the whole matrix by the determinant. So A inverse is 1 over AD minus BC times the matrix with first row D, negative B, and second row negative CA. If instead the determinant is 0, there is no inverse, the matrix is singular, and you cannot divide by 0. You can verify the formula by multiplying A by this candidate, the off-diagonal terms cancel, and the diagonal terms each become AD minus BC, which the fraction turns into 1, giving the identity. The determinant is doing the deciding here, and that is our preview of the next episode, one number that says yes or no to invertibility. Why should one number, the determinant, decide everything? Here is the geometry. For a 2x2 matrix, the absolute value of the determinant is the area of the parallelogram spanned by its two columns. Now think about what that means. If the determinant is nonzero, the two columns are not parallel, they span the full plane, and the transformation carries area to area without crushing anything. Every output came from exactly one input, so the map is reversible. But if the determinant is 0, the two columns are parallel. The parallelogram has collapsed to a flat sliver of 0 area, and the transformation squashes the entire plane down onto a single line. Once space has been flattened, many different inputs get mapped to the same output, and there is no way to tell them apart afterward. The information is gone, and no inverse can bring it back. That is the deep reason a singular matrix can't be undone. It destroys area, and the determinant is exactly the detector that measures whether that destruction happened. For matrices bigger than 2x2, we need an algorithm, and Gauss-Jordan elimination gives a beautiful one. Start by writing A and the identity side by side, separated by a bar. This is called the augmented matrix, A bar 1. Now row reduce, using the same elementary row operations from our elimination episodes, but apply it across the whole wide matrix at once. Drive the left block toward the identity in reduced row echelon form. If you succeed, if the left block becomes the identity, then the right block has magically turned into A inverse. The block A bar I has become the block I bar A inverse. If instead the left block can never reach the identity because a row of zeros appears, then A is singular and has no inverse. Why does this work? Each row operation is secretly a left multiplication by an elementary matrix. Reducing A all the way to the identity means some product of those elementary matrices times A equals the identity, so that product is A inverse. And applying the very same operations to the identity builds exactly that product. The identity records the steps are the inverse. So when, exactly, is a matrix invertible? The remarkable answer is that a whole list of conditions all stand or fall together. For a square n by n matrix A, the following are either all true at once or all false at once. A is invertible. The determinant of A is nonzero. The system A times x equals b has a unique solution for every right-hand side b. The only solution to A times x equals 0 is x equals 0 itself. The columns of A are linearly independent. The columns of A span all of Rn. A row reduces to the identity. Equivalently, it has full rank n, and A transpose is invertible too. 8 statements that look completely different, about determinants, about solutions, about columns, about rank. Yet they are secretly the same statement. Each one is a different way of saying the transformation loses no information, nothing collapses, nothing is thrown away, every output traces back to exactly one input. Memorize the theme even before the details: full rank, non-zero determinant, independent columns, unique solutions, one condition wearing many costumes. The fact that all those conditions are equivalent has a name, the invertible matrix theorem. It says these statements are logically the same, so if you can verify any single one, you instantly get all the others for free. Think of it as a dozen different doors that all open into the same room. It helps to remember them in 2 clusters. One cluster is about existence and uniqueness of solutions. The system has a unique solution for every right-hand side exactly when the columns are independent, which holds exactly when the only solution to A times x equals 0 is 0. The other cluster is about coverage. The columns span the whole space exactly when the determinant is non-zero, exactly when the rank is full. And the contrapositive is just as powerful. If any single condition fails, the matrix is singular and every condition fails. This theorem is the hub of the entire first half of linear algebra. Rank, span, independence, determinants, solvability. Nearly every result we have built and will build connects right back to it. A few properties of inverses earn their place in memory. The most important is the inverse of a product. The inverse of A times B is B inverse times A inverse, in reverse order. In reverse order. Think of it as socks and shoes. In the morning you put on socks, then shoes. To undo it in the evening you take off the shoes first, then the socks. Likewise, A times B does B then A. So to undo it you must undo A first and then undo B. Reversing the order is essential because matrix multiplication doesn't commute. Next, the inverse of A transpose equals the transpose of A inverse. Transposing and inverting can be done in either order. A few more. Inverting twice returns the original matrix, so the inverse of A inverse is just A. Scaling a matrix by a non-zero number C inverts to dividing by C. The inverse of C times A is 1 over C times A inverse. And the determinant of the inverse is the reciprocal of the determinant, which makes sense, since undoing a transformation that scaled area by some factor must scale it back by the reciprocal. Here is the inverse as a round trip. On the left, the unit square sits on a grid with one corner marked so we can track orientation. The arrow labeled A carries it to the middle, where A has rotated and stretched it into a tilted parallelogram. Then the arrow labeled A inverse carries that parallelogram to the right, where it lands back as the original unit square, corner mark and all, identical to where we started. That is the whole meaning of A times A inverse equals the identity. Go there with A, come back with A inverse, and every point returns home. Underneath, the cautionary case. If A had instead flattened the square onto a single line segment, a determinant of 0, there would be no way back because the whole square got crushed onto that line and the area was destroyed. That collapsed picture is struck through, the visual signature of a singular matrix. Reversible transformations preserve area, the ones that flatten it cannot be undone. Let's watch the algorithm in motion. We see 3 snapshots of the augmented matrix, each split by a vertical bar into a left block and a right block. In the first snapshot, the left block is our matrix A, and the right block is the identity, sitting quietly beside it. Then we row reduce, and the second snapshot catches the process midway. The left block is partly cleaned up, perhaps upper triangular, while the right block has filled with new mixed entries. Every operation we do on the left, we also do on the right. In the third snapshot, the left block has become the identity, all ones on the diagonal and zeros elsewhere. And at that exact moment, the right block has transformed into A inverse. It is as if the identity started on the right and slowly traded places, the original matrix dissolving into the identity while the identity blooms into the inverse. Every row operation that simplifies A is quietly assembling the undo transformation on the other side of the bar. Reduce the left to the identity and read your inverse off the right. Let's use the 2x2 formula. Invert the matrix A with first row 4, 7 and second row 2, 6. Step 1, the determinant. 4 times 6 is 24, 7 times 2 is 14, and 24 minus 14 is 10. The determinant is 10, which is not 0, so A is invertible. Step 2. Apply the recipe, swap the diagonal entries 4 and 6, negate the off-diagonal entries 7 and 2, and divide by the determinant 10. That gives 1/10 times the matrix with first row 6, -7, and second row -2, 4, in decimals, first row 0.6, -0.7, and second row -0.2, 0.4. Always check. Multiply A by this inverse. The top left entry is 4 times 6 plus 7 times -2, which is 24 minus 14 equals 10. The off-diagonal entries cancel to 0, and the bottom right also comes to 10. So A times A inverse is 1/10 times 10 on the diagonal, which is the identity. Confirmed. Now a 3 by 3 by the Gauss-Jordan method. Invert the matrix A with first row 2, 0, 0, second row 0, 1, 3, third row 0, 0, 1. Write A on the left and the 3 by 3 identity on the right, separated by the bar, and reduce the left block to the identity. The first row has a leading 2, so scale that row by 1/2 on the right, its leading one becomes 1/2. The second row has a stray 3 in the third column, so subtract 3 times the third row from it, on the right, that puts a -3 in the second row. The third row is already clean. The left block is now the identity, so we read the inverse off the right. First row 1/2, 0, 0, second row 0, 1, -3, third row 0, 0, 1. Notice how the inverse undoes A exactly. A scaled the first axis by 2, so the inverse scales it by 1/2, and A added 3 of the third coordinate into the second, so the inverse subtracts it right back out. Last example, a matrix with no inverse, so you recognize the failure. Try to invert A with first row 1, 2, and second row 2, 4. First the determinant, 1 times 4 is 4, 2 times 2 is 4, and 4 minus 4 is 0. The determinant is 0, so A is singular and has no inverse, full stop. Let's watch the Gauss-Jordan method fail to see what singular looks like in the algorithm. Augment A with the identity, then subtract 2 times the first row from the second row to clear the lower left entry. On the left, that wipes the entire second row to zeros. A row of zeros on the left block means the left can never become the identity, so the procedure halts with no inverse, confirming what the determinant told us. And the geometry is visible right in the matrix. The second column, 2, 4, is exactly twice the first column, 1, 2. The columns are dependent. They both lie along the same line, so the transformation crushes the whole plane onto that line. Information is destroyed, there is nothing to undo. A short history. The idea of undoing a system is older than the matrix itself. Around 1750, Gabriel Cramer published his famous rule for solving systems as ratios of determinants. The inverse was hiding implicitly inside those formulas, even though no one wrote a matrix yet. In the early 1800s, Carl Friedrich Gauss developed systematic elimination while computing the orbits of asteroids. That elimination is the very engine that drives the augmented matrix method, turning a bar I into I bar A inverse. Then, in 1858, Arthur Cayley, in the same memoir that founded matrix algebra, defined the inverse explicitly and wrote down the 2x2 formula as a piece of that algebra. The fully reduced version of the elimination procedure picked up the name Gauss-Jordan, after Gauss and the geodesist Wilhelm Jordan, who popularized it. So the inverse arrived in stages, first as ratios, then as an algorithm, and finally as a clean algebraic object you could name and manipulate. Let's recap. The inverse of A, written A inverse, is the matrix that undoes A. A times A inverse equals the identity, and A inverse times A equals the identity. When it exists, it solves systems at a stroke. The solution to A times X equals B is X equals A inverse times B. For a 2x2 matrix, the formula swaps the diagonal, negates the off-diagonal, and divides by the determinant, AD minus BC, and it works precisely when that determinant is non-zero. For any size, the Gauss-Jordan method augments A with the identity in row, reduces until the left block becomes the identity, at which point the right block is A inverse. A row of zeros means the matrix is singular. A matrix is invertible exactly when its determinant is non-zero, its columns are independent, and systems have unique solutions, all one condition gathered in the invertible matrix theorem. And keep two properties. The inverse of A times B is B inverse times A inverse in reverse order, and the inverse of A transpose is the transpose of A inverse. Next episode, the determinant itself, the single number that has been quietly deciding everything. Today we met the inverse of a matrix. The inverse of A, written A inverse, is the matrix that undoes A. A times A inverse equals the identity, and A inverse times A equals the identity. When it exists, solving a system becomes trivial. The solution to A times X equals B is just X equals A inverse times B. For a 2x2 matrix, there is a formula. Swap the two diagonal entries, negate the two off-diagonal entries, and divide everything by the determinant, which is a times D minus B times C. The inverse exists exactly when that determinant is not zero. For larger matrices, we use the Gauss-Jordan method. Write A next to the identity, forming the block A bar 1. Then row reduce until the left side becomes the identity. The right side has become A inverse. A matrix is invertible exactly when its transformation loses no information. When the determinant is non-zero, the columns are independent, and A times X equals B has exactly one solution for every B. These conditions are all the same condition collected in the invertible matrix theorem. Two properties to keep. The inverse of A times B is B inverse times A inverse in reverse order, and the inverse of A transpose is the transpose of A inverse. Next episode, the determinant itself, the number that decides it all. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.